Thank you very much for the time and for listening the next 25 minutes. So I've been asked, and what I want to do is to give you an overview on the status of gravitational wave modeling from binary neutron star sources, of course, and in particular some of our recent work. Let me start with a brief overview and introduction. I guess you know most of these things, let's say, but it's good to recap a bit. So as you probably know, by the time the binary enters the frequency band, say, of LIGO and Virgo, the motion has circularized and it proceeds through merges in minutes time scale. So it's about 1,000 orbit. Finally, this object merge and fuse. And if the remnant does not prompt collapse to black hole, then its dynamics is characterized by a short dynamical phase, which is entirely driven by gravitational wave emission. And after that, if it still survives, there's a subsequent circular evolution on longer time scale, which is, broadly speaking, driven by two effects, so neutrino cooling and viscous effects. And viscous effects can be, for example, generated by MHD process or also neutrino themselves. So also in this later phase, one expect also large mass ejections in forms of wind, which has been studied quite a lot in the literature. And one thing that I want to point out that, for example, as a result of this large mass ejecta in winds, a remnant with initially, say, a baryon mass corresponding to an equilibrium hypermassive neutron star can actually become stable and rigidly rotated. So this is a sketch of the expected signal as we understand it today. Essentially, at the considered frequency, what we witness is a transition from the quasi-circular adiabatic motion that we know from, say, post-Newtonian perturbation theory or formalism to a fast motion regime, and then the contact of the two stars and the merger. This is followed typically by a burst if there's a remnant at the kilohertz frequency, which you see clearly in this picture. And that corresponds to the early, I would say, dynamical phase of the post-merger dynamic. So a comment here is that if your goal is to model the signal, you should notice that one of the main difficulties is to put together all these different regimes. So somehow this is different from, say, the LIGO-Virgo black holes, for which numerical relativity essentially can give us, in principle, the answer and the exact waveform. Here is not possible just with a single approach and a single method to obtain such an exact waveform. So the problem might be some more similarity with the black holes in Lizard band. You can figure out if you scale and shift the mass appropriately, then you are more or less in that regime. But still, here we want to talk about binary neutron star. So let's try to specify the problem. So if you want to model the full spectrum that we have sketched before, it should be clear that we need a few things to understand and to work on. So first of all, we need a sort of connection between post-Newtonian regime and the fast motion regime. So this is currently possible only using the Fetting one-body formalism that I will shortly present next slide. We also need to identify key parameters that can capture the merger and the remnant dynamics. So if you think that we simulate this system as a fluid, so there's a four velocity pattern, there's a physics input model for the equation state, and so on and so forth. These things are not, well-defined parameters, sorry, that one can measure in a gravitational wave detection. And from another perspective, you can say the same thing, saying that we need to have this parameter in order to make a predictions of the. So another thing that we need to consider is that in most of the interesting cases, we have some precision constraints. So if we aim at using these models for, actually doing fundamental physics and say something really profound on the system, then it's not enough to have, just a global picture in mind, but we need to precisely quantify this parameter and the signal related to this parameter. So I hope to cover some of these aspects in the talk. So what we currently use to model binary neutron star spectrum is actually the EOB formalism, and this we use to precisely to connect the different dynamic regime and to identify the some of the key parameters that can, really capture the merger dynamics. So at the analytical level, this formalism exploit various so-called resummation techniques that essentially try to improve the convergence of the post-Newtonian asymptotic series, and the latter is included as a appropriate weak limit of the formalism. The EOB formats also include perturbation theory. So when you expand in the mass ratio limit, you do recover what you expect for the test mass. So from there, you can extend concepts like a last stable orbit or so on to the comparable mass case, and this indeed is a powerful way to grasp things for the merger. So moreover, these formats can somehow extend to the fast motion regime. So thanks to these techniques, and you can in fact extend it at least qualitatively through merger, and you can get the right qualitative behavior. So once you are there, of course, you can compare with simulation and try to complete the information with those. So perhaps something to mention here very quickly is that beside the post-Newtonian approximate, all the tidal waveform models that are currently used for aLIGO-aVirgo analysis are in a way or another based on this formalism. Okay? So there's not much room to play with. So I don't want to give you many details here, but let me come immediately straight to the point. So how does current waveform perform if we are looking now for design sensitivity and to measure in particular the tidal parameter? So in figure, you see the result and the outcome of a so-called injection study. So it's a mock study in which we use 3 waveform model, and we simply compare what they would predict in an actual parameter estimation analysis. And the result is that for the loudest and most informative events, there will be systematic bias just introduced by the waveform approximate. So in particular, what you see is for many different models at the increasing value of the tidal parameter, the deviation with respect to the injected value and the one recovered by other waveform. So in practice, this number could translate in a rough estimate of the radius uncertainty, which is about 500 meters, which is well above what people would like to measure, let's say. Yeah, so there are other approximates with respect to those used here, but the situation doesn't really change. So for some approximates are closer, of course, to each other, but simply pushing to slightly higher signal to noise ratio, it will give you the same. It will give you the same the deviation. So basically, the take home is that perhaps excluding post-Newtonian approximation, which you might not want to use at very frequent, no way to know which waveform is more correct. And so this will be, say, a projection of what will happen, not in 10 years, but just a design sensitivity. The good news is that we do understand what's the origin of these differences. So we might not know what's the exact waveform, but we can study this waveform very in detail and understand which physical component, let's say, which part of the interaction gives you gives you these differences. So in this game, something that one has to take into account and always think about is at which frequency a certain parameter is measured. Okay, and the curve in this plot it's perhaps technical, but it precisely indicate where the information is for different parameters. So you see that chirp mass, for example, is measured at very, very low frequencies, whereas tides are measured at higher frequency, and you might expect this because tides are short-range interactions. So yeah, so you might expect that these are measured better at higher frequency. And so basically, in a situation like 1708-17, you do measure all the approximate degree in the chirp mass, and you do measure very well the chirp mass. And the reason is that this measurement is performed at frequency which correspond to the post-Newtonian regime, where all the approximate kind of agree and can give a precise measure. But they instead disagree in estimating the tidal parameter, since the phase evolution at higher frequency disagree and can disagree significantly. So this particular figure is produced, just for completeness, for ISNR, which is not the case of 1708-17, but again, it is also possible to make this reasoning also for cases to lower SNR, and the conclusion are more, of course, more involved, but rather similar. Okay. So since the approximate differ mostly at higher frequency, one might wonder if it can use simulation and numerical relativity to kind of fix or determine these differences. And so to answer this, we have actually analyzed if numerical relativity itself can produce faithful waveform using multi-orbit, multi-resolution, multi-orbit runs. And well, what we find is that at SNR about 80, which is just for reference 1708-17 at design sensitivity, basically, numerical relativity is not enough, cannot deliver at the moment enough faithful waveform in order to be used, say, to actually inform a model and be called, let's say, exact. Okay, so in this table, there's just various runs. The number in the second column is basically the resolution that resolves single star in the binary, and F is the faithfulness, and these are different SNR, different faithfulness criteria at the given SNR. And at the moment you have a cross, it says that certainly the waveform are not faithful enough. The moment you have a tick, a positive tick, it means, so it's the other way around. The moment you have a tick, you can certainly say that the waveform is faithful. The moment you have a cross, this is just a necessary condition, but not sufficient for the waveform to be faithful, which means that basically the waveform could be good, but you cannot, but you don't really know. So on average, this seems to suggest that one cannot really trust at the moment the precision of numerical relativity waveform, and there's much more work to do, and also appears to be urgent, because as I said, we could have soon a very nice signal where in principle we could extract high precision information about tides. So I want to move now to the merger and perhaps beyond. So one question that perhaps a naive question, but not so naive, that you can ask yourself is, okay, at what frequency a binary neutron star with some given parameter is merging? And this, so when the spiral is finished, when I can say that there's no more chirp signal, but something else might start. And related to that, you can ask, okay, what's the angular momentum? What's the binding energy and up to this point of this system? Okay, so the answer is basically in this plot that are an example of how one can combine some analytical insights with numerical relativity simulations, and they are made this way. So from the analytical side, the EOB approach suggests that it is possible to qualitatively characterize the merger dynamic just using a single tidal parameter, which is there also in the Newtonian limit. So you use, so this is the x-axis of these plots. This kappa parameter, which is similar to this reduced tidal parameter that most of you are used to. They have almost the same meaning. And so you take this seriously and you try to analyze simulations in terms of this parameter. And you do find that there's a very strong correlation of every quantity essentially into this parameter. And by using the simulation data, you can actually extract quantitative description of every, I would say, physical interesting quantity at merger. So this plot, this relation always go under the name, quasi-universal relation, or EOS, insensitive or independent relation. And just for the young people in the audience, I want to remind you that this is, yeah, it's perhaps not the proper way to think about those. So of course, the equation state information is there, and it's precisely in this tidal parameter. What one really means is that all the information that comes to the equation state, the equation state brings, is just summarized by this order parameter, which is the tidal parameter. So these relations are not really just a theoretical observation. Of course, you can predict exactly where the merger frequency is with those, which is useful for waveform modeling and for analysis, but they also are useful in general to make prediction about the remnant. So in particular, the binding energy at merger is a sort of lower limit for the total energy that you can emit in gravitational wave. And here you have, a complete description of this lower limit. And at the same time, a quantity like the angular momentum at merger is some kind of upper limit on the black hole spin or on the remnant rotations. So it can give you some meaningful quantitative estimate. So moving beyond merger, the first thing that one might want to know is if it's possible to predict in advance, from whatever inspiral parameters, if a binary will collapse or not immediately to black hole. And there are many results in literature. There are several approaches, and just summarizing some of those. So first approach is based on the consideration that the fact that a remnant prompt collapse to black hole might somehow be related to the maximum mass that can be supported by the given equation state. And well, one can postulate that there's a linear relation and look for the constant of proportionality. And it turns out that this is not a constant, of course, but it can be parameterized rather accurately in terms of spherical stars quantity for the same equational state. And this is an approach that has been taken by various authors, and seem to be successful, at least for comparable masses, and say equal masses merger. There's a second approach. You can learn something from the prompt collapse if you study the gravitational wave luminosity. In fact, this was a byproduct, sort of. So again, this plot shows the peak luminosity of the gravitational wave, the binary neutron star merger, again as a function of the tidal parameter. You see, you can describe it just using that and the mass ratio. You can nicely describe the peak luminosity of this object. This is exact. This is from the simulations. Okay, and the second information is that the purple simulation are all simulations that produce immediately black hole. Okay, and so you see that there's a sort of threshold that's small, small values of the tidal parameter for which all the purple dots accumulate, and you can write up easily a threshold by looking at this data, which is only based on the tidal parameter and the mass ratio. So the physical intuition behind this model is that essentially the tidal parameter gives you a measure of the binary compactness, and so the more compact, the closest you are black holes formation. So this model, okay, this model can be actually used to infer something and quantitatively from the inspiral gravitational wave, and here we have used actually both. And just from the parameter, you can use this relay from the parameter that you infer from the inspiral, so masses and so on. You can use these numerical relativity relations to actually tell what's the probability of prom collapse. So it's a relatively straightforward exercise with the posterior from the gravitational wave analysis. And you've applied this to the two events that we have. So in case of 1904-25, what we find is that the black hole is formed almost certainly, which is kind of expect given the high mass of the system. But here we can of course compute the actual probability of it given the models. More interesting is the case of 1708-17, for which both criteria alone would give a 50-50 chance of prompt collapse formation. But if you include additionally the constraint from the maximum mass for the neutron star from the pulsar observation, you then actually get that the prompt collapse probability is less than 10%. So this is, let me stress that this is obtained only from the analysis of the gravitational inspiral data. Okay, so you don't really need to observe the merger for that. And if you compare this small probability with the actual various astrophysical interpretation of the counterpart, you see this quantitative result supports, the fact that the remnant was actually at least temporarily supported by pressure, and they did not prompt collapse immediately. So the question now is if we are happy with this model. So the answer is no. If you consider simulation of high mass ratio, as we have recently performed, so we went up to 1.8, which is rather large for binary neutron star. In this merger, we saw that the primary star can be very massive, in principle, depending on the chirp mass, and the companion can be kind of fluffy star and can disrupt that merger and accrete on the primary. So this mechanism can cause prompt collapse, and it is different from the usual, let's say, the usual way. So that's why we refer it as accretion-induced prompt collapse. And this plot show again the mass criterion in some sense, so the mass of the binary versus the UV compactness of the star, where the solid line is the threshold criteria for the prompt collapse, and everything that is prompt collapses according to this model should stay above this solid line, whereas you see that the prompt collapse data that are the ones circled in black are almost all below these lines. These are high mass ratio, and so this just says that the criteria does not work if you have this kind of situation. The dash and dot line are simply the threshold mass lowered by substituting, in an attempt, the chirp mass, and you see it gets better. So it suggests that improved model models could be improved by including the mass ratio that would lower this threshold. So the tidal parameter criterion also, differently from this one, contains the mass ratio. So you might hope that would work better. It does, but also in this case, it's not possible to explain all the simulation. So my take home on this is that while both criteria that I've presented are physically motivated, they might be not fundamental one, and certainly are not adequate for say, a very large mass ratio object, which we might observe. I'm not sure how I'm with the time, but
I think it's over. So we
okay.
The conclusion quickly, but also there will be some extra time later for the talk of Richard. So
okay, then let me just conclude. So the last part that I wanted to talk about was actually Postmerger, And the message is that this merger parametrization can be extended to describe the post-merger frequency and the main peaks. There are physical reasons behind that. And well, what we have now is a model that is built from an EOB-completion from a completion of the EOB model at high frequency that's fully informed or fully taken from numerical relativity. And we do have available complete waveform model that can predict the whole range of frequencies. And there are many aspects they can be used, of course, for interest in physics, but perhaps we talk another time about that. There are many directions that in which we have to improve these models, because we do aim at building something that is quantitative, and that would allow us to do this precision physics, and in particular thinking about equation state constraints. Okay, thank you. Sorry for taking too long.
Oh, thank you very much for this very complete talk on gravitational waveforms modeling. Please ask your question. There is time for a quick question, and there will be time for more question after Richard talks, since Richard talks is going to last a little bit less than the time we planned. So please raise your hand for a quick question now. Okay, Vasily, ask your question.
Hello, very nice talk. So when you're saying that in order to get to SNR 80, what do we actually need from the numerical point of view? New methods, more computational resources, or a combination of them?
Yeah, I would say a combination of them. So where the data falls short is really the last orbit, which of course we didn't test in the past much, because we were very happy of getting good agreement over several orbits, and perhaps we didn't care about this, last one orbit or last one cycle, in which we do see that there are differences between analytical model and numerical relativity. But at the same time, we know that the numerical relativity error are much larger, and you cannot. It's very hard to control those. So you change few things. It's completely hydrodynamical dominated. So you do expect, and you can in part measure those, and they are much larger error. So I think I would say it's a combination of those. So we would like to have longer, more precise simulation, and measure better the error. And once you have all this, in order to have all this, you do need to have codes that are that show better scaling. So just not to remain vague, the order of magnitude, we start to see some good waveform once we have order 250, 300 points per star, roughly, at the beginning. Of course, then it changes because we have mesh refinement. But so these are so the current simulation for waveform production are there are very few that reach these resolutions.
Okay.
Thanks.
Thank you. This is very good indeed. I think this is one of the topics I would like to have discussed in the afternoon, about what we need to do in order to do faithful simulation. Okay, so given that we have no time, I would say we stop the recording